Hello everyone, this is Sanjay from CSIT branch. Today, my tech talk of computer organization architecture topic is low contention semaphores and ready lists. Let's jump into introduction. A method for reducing semaphores and ready list contention in multiprocessor operating systems is described. Its correctness is established. Its performance is compared with conventional implementations. A ready list implemented as a ring network is proposed and evaluated. So before going into our topic, let's we going to know about semaphores. In computer science, a semaphore is a variable or an abstract data type used to control access to a common resource by multiple threads and avoid critical section problems in a concurrent system such as multitasking OS operating system. The problem: the process manager is the component of an operating system's kernel that implements concurrent process and semaphores. Its simple interface to the rest of the system includes the wait and signal operation on semaphores. The detail of starting, stopping, and scheduling process are hidden inside the processor manager where they cannot affect the rest of the system. The standard designs of a processor managers are based on the single processor, that is CPU. It is multiplexed among many processors 1, 9, 14, 16. These designs can support only a few CPUs before overhead and lock contention becomes too severe. Two factors degrade a process manager's efficiency: primitive operation times and busy waiting. Our design reduces operation times to the minimum by tightly coupling the hardware architecture and software data structures. This permits the primitive operation of the process management to the fast microprograms in each processor instruction set. We will compare standard implementations of wait and signal with our proposals. For a large number of processors, a more radical approach is needed. We will show that ready list contention and the multiprocessor priority problem can be virtually eliminated by implementing the ready list as a circulating ring of processor indices. Overview of the process manager. The process manager is the portion of the operating system that implements processes and semaphores. It hides the details of scheduling and of switching processors among the processes. It performs the wait and signal operations on semaphores. It creates and deletes the processes and semaphores. Our process manager has two levels. The lower level implements the primitive operations for waiting, stopping, and scheduling a processor on a processor. The upper level implements the wait, signal, create, and delete operations. This division permits changing the architecture of the processors or data structures without reprogramming the upper level operation. The data structure. The internal data structure of the process manager comprises the process list, the ready list, and the semaphore list. And in this diagram, we are going to see the process manager device structure. It is the ready list consists of the head, tail, and lock, and it is the semaphore consists of the count, head, tail, and lock. Here we can see the process manager data structures. The ready list is a queue containing indices of all processes enabled to run on a processor. It, it emanates from descriptor containing a head, tail, linked list specifier, and a log bit. The queue itself is the chain of processor founded by tracing through successive link fields starting from the head processes and terminating at the tail processes. The link fields of both the tail process and process 0 are always 0. The log bit is used to restrict access to the ready list to at most one processor at a time. The semaphore list is an array of semaphores descriptors, each containing a count field registering the excess of sent over received signals. A head tail linked list specifier defining a queue of process waiting for signals, and a log bit to prevent simultaneous access by two or more processors. Locks. The foregoing definitions shows a log bit in the ready list descriptor and in each semaphore. descriptor. These bits must be set while any processor is used to associated data structure. They are using lock instruction and a reset using unlk unlock. Let memx lock denote the bit of the memory word at address x used for lock. The microprogram for lock x follows the schema. Here we can see the above said that a lock unlk pair is intended to enclose a critical section of instructions while a processor is inside a critical section. Its interrupts must be shut off by a disable instruction to guarantee that it cannot be diverted until it has completed the critical operation. Starting, stopping, and scheduling process. At the lower level of the process manager, there are three uninterruptible operations for manipulating the process list and the ready list. This operation refers to the processor register self that contains the process index of the processor currently running on that processor. Says WL used to stop a process from running. These processor registers are copied into PL self stateward with L replacing the value of the instruction pointer. Loads FW used to start a process running removes the head process from RL and sets self to this value. Loads the processor registers from PL stateward and proceeds. Ready I used to schedule a process inserts process index I at tail of the RL. And this is wait and signal operations. The wait and signal operations are in the upper level of the process manager. The wait operation is used to receive a signal from a semaphore. The calling process is delayed if the count is 0 or less at time of the attempted reception. The signal operation is used to transmit a signal through a semaphore. The waiting process at the head of the list is released if the count is less than 0 at the time of the attempted transmission. Both operations must be indivisible in the sense that while a wait or signal is in process on a given semaphore, no other wait or signal on the same semaphore may be initiated. This implies that both operations must be uninterruptible. A program for the wait operation is interruption handling. Interrupt handling. A fault is an error condition detected by the hardware of a processor. It triggers a procedure called within a current process to a routine that attempts error recovery. An interrupt is signal from a device to its driver process requesting more work. It triggers a context switch to the device driver process. Creation and deletion. The process manager must provide for the creation and removal of process and semaphores. This can be done with the two pairs of the program. Here down we can see the program. And the correctness. We will outline an argument to prove that the implementation is correct. The objective is to show that the process indices properly traverse the states of the diagram in the next figure. And this is the figure where we can see the process state transition diagram. And finally, the solution. The weight and signal overheads in the worst case analysis are sufficiently high that communications among operating system process, which may occur from 100 to 300 times per second, cannot be handled efficiently by programs such as the given earlier. These operations must be incorporated into the machine's instruction set. And this is a semaphore with tag, count, and head and tail lock. Semaphore words. Suppose that each word of memory contains a tag field containing the type of information stored within. Suppose that a semaphore is implemented as a semaphore word and that the wait and signal operations are part of the instruction set of each processor. For this environment, then the instruction wait X and signal X operate on semaphore words stored in memory X. These instructions are uninterruptible because their microprograms do not examine interrupt indicators. Tagging permits distributing semaphores throughout data structures without endangering the integrity of wait and signal operations. Tagging increases software reliability by preventing locking operations from being applied to non-semaphore locations. Note, however, that is type checking compiler also provides the same advantage for this application. Tagging is more convenience than a necessity. Conclusion: we have demonstrated that the modest amount of hardware support can significantly reduce the space and time requirements of the primitive operations for process context switching and semaphore management. The proposed wait and signal operations are roughly 1 by 180 thus 1 in 180 the space time of the corresponding IBM 370 implementation and roughly 1/40th the spacetime of the corresponding VAX implementation. The proposed implementation reduces ready list lock holding times to 4 memory reference times. These operations are efficiently enough to permit process management without shortcuts and to permit a greater number of processors to be used. Our results can be applied to any system in which a set of identical processors has access to shared memory. This is true of many large mainframe computer systems. It will also be true of single-user multiprocess operating systems, example Bell Labs Unix. On a personal computer, additional CPU boards can be plugged in, much like additional memory ports, to improve performance. And these are references of my given topic. Thank you.